Hi guys, so today we're going to talk about angle sum and difference identities for sine and cosine. The basic idea is the following. First of all, I want to show you that the sine of the sum of two angles, like the sine of A plus B, where A and B are two different angles, is not, unfortunately, equal to the sine of A plus the sine of B. A quick comment on this. One way of thinking about this is that the sine doesn't distribute over plus. Students think that everything in math distributes. The truth is that very few things actually do. And the sine function definitely does not distribute over sums. And to see that this is true, all I have to do is show you a counterexample. And it's pretty easy to find one. It almost never works. If I choose angle A to be pi over 2, and I choose angle B to be also pi over 2, we'll see that the sine of A plus B is not, in fact, equal to the sine of A plus the sine of B. So let's have a look. So the sine of A plus B would be the sine of, well, as I said, we're letting A and B both be pi over 2. That would be sine of pi over 2 plus pi over 2, which, of course, is the sine of, well, pi over 2 plus pi over 2 is just pi. So we have the sine of pi, which hopefully you remember is 0. Okay, so that's the sine of A plus B. Let's consider the sine of A plus the sine of B. As we'll see, we don't get 0, we get something else. Okay, so sine of A, that's sine of pi over 2, plus sine of B, well, B is also pi over 2, so sine of pi over 2 again. Hopefully you remember the sine of pi over 2 is 1, so that's 1 plus 1 again, which is 2. And as you can see, these two things are not equal, therefore the sine of A plus B in general is not equal to sine of A plus sine of B. So the sine function doesn't distribute over plus, and you're probably not going to be surprised to find that it doesn't distribute over minus either. So the question is, if this isn't the rule for the sine of the sum of two angles, then what is? Is there a rule for when we have two angles being added or subtracted inside of a sine or a cosine function? Is there some identity that we can use? And there is. So that brings us to the angle sum and difference identities. So what are they? So here they are. So we have the cosine of A plus B is equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. So there is a formula for the cosine of one angle plus another, but it's probably not what you were expecting, right? And there's also a formula for the cosine of A minus B. It's very similar. It's cosine of A times cosine of B plus the sine of A sine of B. So these two formulas tell us what happens when we have the cosine of the sum of two angles or the difference of two angles. If you notice, these two formulas are very, very similar. The only difference is that when there's a plus here, there's a minus here, and when there's a minus here, there's a plus here. Because of that, we often condense these two formulas into a single formula and simply write the cosine of A plus or minus B is equal to the cosine of A times the cosine of B, and then I'm going to write something a little strange, minus plus sine of A sine of B. And this is how I'll usually write this formula. This formula is the previous two formulas condensed into one. And the way that you're supposed to read it is the following. Notice how there's a plus on top and a minus on bottom here. And then over here there's a minus on top and a plus on bottom. What that means is that if you have a plus in between the two angles, then you're going to put a minus in between these two terms here. On the other hand, if you have a minus, right, in between the two angles, like A minus B, that means you're going to put a plus in between these two terms here. So this is just a condensed way of expressing these two formulas. So that's the sine difference formula for cosine. Let's take a look at what it is for sine. For the sine, I'll just write down the condensed version. So the formula for sine is the following. It's the sine of a plus or minus b is going to be equal to the sine of a times the cosine of b plus minus the cosine of a times the sine of b. Okay. And as before, you know, this formula really is two different formulas condensed. One is for when you have the sum of two angles, and the other formula is when you have a difference. So if you're looking at the sine of a plus b, that means you've got a plus here. So what do you put between these two terms, a plus or a minus? Well, there's a plus on top here and a plus on top here. So when you have a plus between these two angles, you put a plus between the two terms. And since there's a minus on the bottom here and there's a minus on the bottom here, that means that when you have a minus between the two angles, you put a minus between the two terms. Now, I'm sure you're wondering where in the world do these formulas come from? The short answer is geometry. The proof of these formulas requires a kind of a pretty complicated construction using some geometry and a bunch of algebra. And I would derive it, but unfortunately we don't have one of the tools that we need yet. One of the tools that we need is something called the law of cosines. We'll deal with that in a later unit, and later on I'll come back and prove this to you, but for now you're just going to have to take this on faith. But we will eventually prove this later on, once we have the necessary tools. Okay, so really quick, you don't have to memorize these formulas, right? As you can see, they're like super, sort of complicated and fiddly. You do not have to memorize these, okay? Unlike previous trig identities, these will be given to you. But you do have to know how to use them. So let's consider some examples, all right? So for our first example, let's consider find the exact value of sine of 15 degrees. Okay? Now, how do you do that? So here's the thing. When I say exact value, what I mean is no calculator, right? You could certainly go to your calculator, type in sine of 15 degrees, and you would get some decimal answer. That's not exact, okay? Sine of 15 has a non-terminating decimal, which means whatever's displayed on your calculator is not exact. So how do you find the exact value of sine 15? The thing to recognize here is that 15 degrees is not a value on the unit circle, right? It's not on the unit circle. And that really presents a problem, right? How are you supposed to know the sine of 15 if 15 is not a unit circle value? It's not 30, it's not 45 or 60 or anything like that. The trick is to recognize that you can represent 15 as the difference of two angles which are on the unit circle, okay? I'll say that again. You can represent 15 as the difference of two angles which are on the unit circle. So the idea is to say sine of 15 is the same thing as sine of, all right, now the difference between what two angles? What if I took 60 minus 45? That's 15, isn't it? 60 minus 45. Now the thing is, what I have here is the sine of the difference of two angles. It's like a sine of A minus B. And I have a formula for that, right? I have a formula for the sine of A plus or minus B. And I can use that formula on this expression, recognizing that A is simply 60 and B is 45, right? So let's go ahead and use this formula. So if I want to use the difference, right, here, notice that I have a minus in between my two angles. So that means I want a minus here, which means I'm going to have a minus in between my two terms here. So what is this going to be? It's sine of A, so that's sine of, what is A here? Oh, it's 60. So sine of 60 times cosine of B. That's cosine of, what is B here? It's 45. It's not negative 45, it's just 45. And then, as I said, since we have a minus in between our two angles, we're going to have a minus in between the two terms, so a minus there. And then it's cosine of A, so that's cosine of 60 times sine of b, that's 45. Now the great thing about this is that every expression in this whole mess can actually be evaluated. Sine of 60, we know what that is. Cosine of 45, we know what that is. Cosine 60, we know what that is. Sine 45, we know what that is. So now we proceed to evaluate each of those expressions, and we will wind up with an exact value of sine 15 degrees. So what do we have? Sine of 60, that is root 3 over 2. Cosine 45, that's root 2 over 2. Minus cosine of 60, what is that? That's 1/2 times sine 45, that's root 2 over 2. All right, so whatever this thing is, that's the sine of 15. I just have to simplify it. So, we're multiplying two fractions, right? So you multiply across the top and across the denominator. What do you get when you multiply root 3 with root 2? If you remember, when you multiply radicals, you just multiply the insides. So that's root 3 times 2, in other words, root 6. Okay. Denominator, 2 times 2, that's 4. Minus. Now what's happening here? Well, again, we multiply across the top. 1 times root 2 is just root 2. Multiply across the bottom. 2 times 2, that's 4. Okay. These two fractions have common denominators, so we should certainly put them together. So that's root 6 minus root 2 all over 4. This expression can't be simplified any further. If you remember, root 6 and root 2, they're not like terms. They can't be combined in any way. It certainly isn't, root 4. It's definitely true that root A times root B is root AB. That's the rule that I was using a moment ago when I computed root 3 times root 2 is root 6. That certainly is true. However, there's no such rule for addition or subtraction. It's definitely not true that root A minus root B is root A minus B. That's false. That's not true. Okay, so this numerator expression just can't be simplified, but that's an exact value for sine 15. And what you can see is that, previously we had a very limited number of angles, basically the unit circle values. Hey, all set? Awesome. Thank you. So basically what we had was a very limited number of angles for which we could actually find exact values, right? 60, 30, 45, and stuff like that. But because of these new formulas, what we've done is we've expanded the number of angles for which we can find exact sine and cosine values, okay? All right, so that's one example. Bye. Let's take a look at another example. Let's do a different kind. Consider the following. It's kind of the same thing, but in reverse. Suppose I told you to find the exact value of, let's say, cosine of 50 times cosine of 10 minus the sine of 50 times the sine of 10. So find the exact value of that expression. Now, exact value means no calculator. If you use your calculator to find cosine of 50, you'll get some answer, but it won't be exact. It'll be, a truncated decimal. So how are you supposed to do this? What you should notice is that this expression, structurally, algebraically, however you want to put it, resembles one of the formulas that we just went over. It's cosine of one thing times cosine of another minus sine of one thing times sine of another. If you go back to these formulas, that looks an awful lot like this formula. Cosine of one thing, cosine of another, sine of the one thing, sine of the other. That's really what we have here. Cosine, cosine, sine, sine. The idea is to recognize that this expression is what you would obtain if you applied this cosine formula to some expression. Okay, that's the idea. Now, my claim is that this whole thing is really cosine of either 50 plus 10 or cosine of 50 minus 10. Exactly which one it is, we have to think there's a minus in between these two terms. And when is there a minus in between the two terms? Okay, the minus is on top here, and the plus is on top here. So that means it's really the sum, okay? So I claim that this is actually equal to the cosine of 50 plus 10. So yeah, so the thing to recognize is that cosine of 50 plus 10, if you applied the cosine sum formula to this angle, then it would spit out exactly this, right? Because the cosine sum formula says if you have cosine of A plus B, then that's cosine A cosine B minus sine A sine B. That's exactly what we have here. If you applied the cosine sum formula, you'd have cosine 50 plus 10 is cosine 50 times cosine 10 minus sine 50 times sine 10. So the thing is, we're really kind of using this identity in reverse. We come across this expression, we recognize that, oh, this expression looks like someone applied this identity to some, in this case, sum of two angles. And we use it in reverse and we say, oh, that's really cosine of 50 plus 10, which of course is cosine of 60, which is something we actually know how to evaluate, right? That's just 1/2, okay? All right, so let's just consider... All right, so let's consider one more example, and then we'll be done. So let's suppose the following. Suppose that sine of A is 4/5, and sine of B is 1/2. Where pi over 2 is less than A and B is less than pi. Okay? Find sine of A minus B. Okay? So that's the question. So what in the world do you do with this? So for one thing, let me just point out, I don't know what angles A and B are. Like, A is an angle whose sine is 4/5. 4/5 is not a unit circle value, so I don't know what angle A is. As it's going to turn out, we don't really need to know what angles A and B are in order to answer this question. So let's just first recognize that the question is asking us to find sine of A minus B, and we have a formula for the sine of A minus B. We might as well use it. It's the... It is the sine of A times the cosine of B minus the cosine of A times the sine of B. So that's the formula for the difference of two angles for the sine function. And what you should notice at this point is that we know what a bunch of these things are, right? We know what sine of A is. It's 4/5. And we also know what sine of B is. It's 1/2. Okay? On the other hand, some of this information is currently unknown. Cosine of B, I don't know what that is. Cosine of A, I don't know what that is. However, it turns out you can find these two things. You can find cosine of A, and you can find cosine of B. And once you do, you can fill these in with their values and then simplify, and we'll be all done. So let's start with cosine of A. How can we find cosine of A? Well, we know that the sine of A is 4/5. So I'm going to do something we haven't done in a while, but should still be pretty familiar. I'm going to basically draw a right triangle and use it to find the cosine of A. So sine of A is 4/5. Now notice this thing here. It says that A and B are bigger than pi over 2 and less than pi. That just means that they're in the second quadrant. Bigger than pi over 2, smaller than pi. So A and B are both here. So let me draw a picture of angle A. Maybe A is this angle right here. And now take this point and draw a right triangle. Now what do we know? We know that the sine of A is 4/5. And we know that the sine of A is opposite over hypotenuse. That means that this side right here is 4, and this side here is 5. That's the hypotenuse. Okay. And we can use Pythagorean theorem to find this missing side here. If I call it x, then what I know is that x squared plus 4 squared is equal to 5 squared. If you solve this equation for x, you'll find that x is equal to plus or minus root 3, right? Or sorry, just plus or minus 3 when you take the square root. Now, is it positive or negative 3? Well, basically the cosine of a, because a is in this quadrant, the cosine of a must be negative, right? The cosine of a is adjacent over hypotenuse. That would be x over 5. That would be negative 3 over 5. Any way you think of it, you should recognize that the cosine must be negative in this region. So the cosine of a is negative 3/5, okay? And now a similar diagram will allow us to find the cosine of b, the other thing that we're trying to find, right? We need to know the cosine of b as well. Similar diagram will give us cosine b. So here's a circle. Let's say that angle B is here. We know that B is in the second quadrant, right? Both A and B are in that second quadrant. So let's say that B is here. Draw a right triangle. What do I know? I know that the sine of B is 1/2. That means that opposite is 1, hypotenuse is 2. So 1 is the length of this side, and 2 is the length of the hypotenuse. Let's call that x. Do the Pythagorean theorem. X squared plus 1 squared is equal to 2 squared. You'll find that x is equal to plus or minus root 3. Now, which one should it be, positive or negative? Well, once again, because angle B is in this quadrant, the cosine has to be negative. It's going to be negative root 3 over the hypotenuse, which is 2, adjacent over hypotenuse, right? Okay, so now that we know cosine of A and cosine of B, we know everything in this expression, we can plug it in and simplify. So let's do that. So I have so sine of A, which is 4/5. So 4/5 times cosine B, which we just established as negative root 3 over 2. So negative root 3 over 2 minus cosine A, which we said was negative 3/5. Negative 3/5. And then times sine B, which we know is 1/2. Okay, so whatever this thing is, that's the answer. We just have to simplify. So multiplying across the top, we have negative 4 root 3. Across the bottom, we have 10. Now, because this minus here, because of this minus and this minus, this term is going to be plus 3/10. Combining fractions, we have negative 4 root 3 plus 3 all over 10. And that's the answer.